How do we tell the stories of cutting-edge materials with limited histories? Can we rely on nanomaterials for a quick fix to societal issues? Using graphene as an entry point, NANOECOLOGIES is a review of contemporary nanomaterial discourses. In a material ecology that is advocated by dominant utopian visions, it's precisely these visions that influences the development of highly advanced technologies, but their realisation is often in relatively rudimentary applications. Mapping of knowledge and production networks creates a framework to problematise these utopian visions as graphene moves through its various scales, from its raw form in landscapes of extraction to the painted walls of ultra-sustainable housing. The rise of nanomaterial usage in daily life inevitably means they are released into the environment in unknown quantities with potentially hazardous effects, thus becoming a unique signature of the Anthropocene.
Countless human activities have causes and consequences measured at different levels and scales. Let's begin by considering the concept of scale. Analysing the spatio-temporal scales associated with graphene allows us to move across its multiple manifestations in an anthropogenic material and frames the wider spectrum of engineered nanomaterials.
What is the scale of research? This map illustrates the conceptual manifestation of graphene by visualizing the global network of knowledge, which is constantly evolving and accelerating. From this, we can see the total number of graphene-related journal articles has increased by more than half over the study period. We can see this is a material of scientific excitement. Researchers are entranced by its promises which are key for graphene to be realized as the wonder material it is framed to be. To localize our analysis, we zoomed in on the UK and specifically Manchester's association with the material. Investigating the observational scale. Graphene was first isolated at the University of Manchester in 2004 in a somewhat rudimentary experiment, which involved the peeling of graphite layers using sticky tape until graphene occurred in its two-dimensional form. The theoretical understanding of a material and their properties at one scale of measurement changes when we seek to understand it at another scale, bigger or smaller. The diagram visualizes a minute observational scale of nanomaterials. Change in physical and chemical properties emerge in materials at this scale. The concept of observation also refers to how nanomaterials are perceived by wider society. The isolation of graphene brought about various claims as a material not just in architecture, but in wider technologies. Utopian visions are key to the nanoecologies. It isn't what we can do now, but what we can do in the future. They invite other researchers to jump on the bandwagon by depicting an exciting and fruitful field. However, these utopian ideas are important to unpack so we can assess the existing reality of the material.
The operational scale refers to the spatial extent of the material as it moves across geographies in its various forms. Using what's happening locally at the university, we wanted to investigate these utopian ideas and began with analysing the material network to production. The University of Manchester sources processed graphene from First Graphene, an Australian company located in Perth, who've pioneered the production of high-quality graphene commercially, which, as they say, is at an acceptable price to the industry. But what is this acceptable price? Deeper investigations revealed First Graphene purchases raw graphite from the Kaha Tagaha Graphite Lanka Limited, the KGLL, a state-owned mining company based in Sri Lanka's lithic landscapes. So the supply of Sri Lankan graphite is driven by the demand of graphene in research and commercial applications. In January 2020, 130 workers at the state-owned KGLL mine struck for 3 days to demand for better pay and working conditions. KGLL was accused of mismanagement of enterprise, leading to exploitative practices affecting local working class communities, and those disproportionately affected were women workers. While the mine workers had previously taken action over their harsh working conditions and called for better pay, they have been systematically dodged by the successive governments in control of the mine. This subordination of working class communities might be multiplied when we analyse the global production of graphite. Sri Lankan exports accounts for roughly 1% of global graphite extraction. It isn't unreasonable to assume that the exploitative practices that are occurring in Sri Lanka aren't also occurring in countries where production is higher. These dirty beginnings begin to contrast the utopian ideas of graphene as a clean end product, highlighting that even these highly advanced materials cannot be produced without these other conditions being in play.
What contrasting stories may architectural applications tell us? To analyse the material, we looked at commercialised products and the associated utopian claims. For example, Graphene paint has idyllic claims of respiratory, thermal conductivity, and durability benefits. Moving away from the utopian ideas of graphene, we wanted to analyse how it is realised within an architectural framework. To understand this, we collected primary qualitative data through an interview which may or may not suggest contradictory stories. In contrast to the dirty realities of extraction in Sri Lanka, the end product is materialised as part of a highly designed world. Our interviewee lives in Europe's first ever retrofit passive house on Zetland Road in Chorlton, Manchester. This is a great showcase for new technologies, but does the domestic reality meet the miracle expectations?
The interviewee was attracted to the virtues and values of graphene paint, with graphene stone paint being specified from a sustainability angle. He was conscious about what he's putting into the house that won't have to be repaired or replaced 5 times. He goes on to note, if we can use materials that are longer lasting and therefore require less maintenance, I think that's sort of the main problem, to make sure the building's still there in 150 years. From this, we became interested in the durability of the paint, which made us wonder about the end of life of graphene.
We analysed the Environmental Product Declaration of Graphene Stone Paint, which is an international certification valid for 5 years. What was curious is that a product that brands itself so heavily on the addition of graphene within its composition fails to declare the impact of the additives, and secondly, that landfill has been assumed as the end-of-life scenario. This is just an example of one product with nanomaterial additives, and from this we can speculate on the development of an accumulating pile of potentially dangerous matter as wider spectrums of nanomaterials are transported from landfill into the natural environment, contaminating the hydrosphere, lithosphere and biosphere.
How does this play out at a human scale? While there are naturally occurring nanomaterials, engineered nanomaterials have found their way into various ecosystems, thus becoming part of a wider anthropogenic nanoecology. Their resistance to transformation and degradation leads to the potential exposure to both humans and non-humans through inhalation, their uptake by organisms from water and sediments, and bioaccumulation. Nanomaterials such as nanosilver are of particular concern as it has the potential to transcend the food chain through trophic transfer. What would it mean if engineered nanomaterials produced by one country contaminated the food streams of another? Where lies the responsibility? This speculation begins to frame the geopolitical issues that encompass engineered anthropogenic nanomaterials.
What does this mean for the Anthropocene? According to expert estimates, up to 500,000 metric tons of engineered nanomaterials are released into the environment annually. We can assume this statistic to be greater than the said estimate due to the reluctancy of manufacturers in revealing accurate figures and the lax treatment of environmental product data as identified in our investigation. Because of this, the effects of nanomaterials become politicized. They are becoming a problem for humans and non-humans across the globe with no specific cause, despite being in the early stages of research. The exploitation of these materials as they move between their varying scales becomes everyone's responsibility.
In 2013, Jan Zalisevich proposed that the growing geological and societal significance of the Anthropocene is now great enough that human-made minerals should be formally listed and catalogued by the International Mineralogical Association. Such a catalogue would allow us to bridge natural minerals with their anthropogenic counterparts and would highlight a distinctive character for the epoch stratigraphy. With this idea in mind, it should be noted that the development of engineered nanomaterials, from the scouring of the Earth's surface through mining to their eventual sedimentation into the stratigraphy, becomes a contribution to the era of human alteration and thus becoming a unique signature of the Anthropocene.
Can we speculate on the nanocene? Our analysis is a speculation on the transformation of the Anthropocene inflecting into what we are coining as the nanocene. This diagram illustrates many positives and negatives of nanomaterials, which are equally weighted to indicate the uncertain futures of the nanocene. On one hand, there is an opportunity to reduce air pollution in megacities through building facade design. However, there is also the militarization of nanomaterials, which gives rise to the question, are we knowingly or unknowingly working with a toxic material which presents a political dichotomy? As we have seen in this presentation, engineered nanoparticles are now present in lithospheres, hydrospheres and biospheres, interacting and interfering with other endeavours. Moving through their various described scales, shape-shifting as they move in and out of human and non-human conditions, formed through human activity but ultimately having a life of their own. Having discussed both utopian and dystopian realities associated with their use, we believe it is too early in the global research of nanomaterials to position ourselves for or against, as all matter has advantages and disadvantages which must be regulated at a political level. The potential multitudinous consequences of engineered nanomaterials are at a scale that is so vast, yet minuscule, while humans, the main actors in the unfolding story of nanomaterials, should remain ambivalent on their role in the wider society.